Hello, my name is Punyapa Titichoatrattana. I came from 1103, and today I'm going to talk about the chapter 20 of the physics class, which is going to be the static and electricity. Let's get started with the chapter 20, or the static electricity. In this chapter, it's going to be separated into two sections. The first one is the electric charge, and the second one is electrostatic force. Let's get started with the electric charge, or the section 1. When we talk about electric charge, we have to know what is electrostatic first. The electrostatics is the study of the electric charge that can be collected and held in one place. From the Benjamin Franklin theory, the charge is separated into two, the positive and the negative. The two objects with like charge are likely to repel each other, and two objects with a like charge are attract to each other. For example, for the positive, if the first object have a positive charge and the second object have the positive charge also, it's going to be repelling each other. But if the first one was the positive and the second one was the negative, they're going to attract to each other. As we can see from the example here, the hair will stand on the end because of the electrostatic force between hair and oppositely charged balloon. Okay, so here's the terms that we have to know. The electron in physics is all material that contain like negatively charged particle, and neutral is amount of a negative charge exactly balanced to the amount of the positive charge. With additional energy, outer electron can be removed, and in the positive, what we have to remember is that the additional energy, the outer electron can be removed. And for the last one, positive is the atom missing electron, and that's going to be the result of it to be the positive charge. Another cause of the particle to be a negative charge is that the free electrons attract to the other atom. Okay, so next one, charge. Charge is a process of transferring electrons, and charge is conserved, which just means that they're never created nor destroyed. It just transfer. For example, here, this is the visual of the lake and the floor. Before the lake is moving, the lake has the positive charge, and it's likely to have the positive charge, and the floor is likely to have more negative charge. But after the lake is moving faster and faster, the electrons from the floor is likely to transfer to the lake. Okay, so next one would be the conductor and insulator. The insulator is the material through which a charge will not move easily, and the conductor means the material that allows charge to move past easily. And the plasma is when the positive charge is equal to the negative charge. The example for the conductor could have been the metal. It is a very good conductor because at least one electron on each atom can move easily. And here's a table that would show some example of the good conductor and good insulator. The good conductor, as I mentioned before, the metal and the water, but the good insulator could be glass or dry air. And here's a visual that shows that the conductor, as you can see, the conductor is like the electron can pass and attract the positive one easily, but in the insulator it's not. Okay, so let's get started with the essential question for the section 1. The first one, how can you demonstrate that charged objects exert force on both on attract and repulsive? So the answer would be that the same charged object would be repulsive, but the different charges object would be attractive. The second one, how do we know that charging is separation, not creation? And the answer is absolutely, because you cannot create charge. We can only transfer it. I'm sorry for my mishandwriting. And the third one, what are the difference between the conductor and insulator? The conductor is the substance that lets the charge move easily, but the insulator will let it go easily. Okay, so let's move on Now to the section 2 of this chapter, it would be the electrostatic force. Let's get started with the force on charged object. There are two kinds of electric charge, the positive and negative, which we already mentioned before. The charge exerts force on the other charge at the distance, and the force will stronger when the charges are closer together. The same charge will repel and the opposite charge will attract. As you can see from the withdrawal in here, this is the withdrawal of the metal, of the magnetic that hang on the first metal that hang on the string, and the second metal that move closer to the one that with the string. After as you can see, their charge is different, and after they move closer, they might stick together, just like if you can remember, when you may play it when you steal, and you may find it also like on the computer. If you put some metal near the computer, it might get stick with it. Okay, so let's move on to the electroscope. The electroscope is a sensitive and useful for is a tool that is sensitive and useful for the determining electrical charge. And this is the part of the electroscope. There's a knob, there's an insulator, there's a leads. And for the way to use the electroscope, the type of charge carried by the electroscope can be determined by observing the leaves when the rod of known charge is brought closer to the knob. There's several ways to charge a neutral object. The charging a neutral body by touching it with the charged body, as shown in the picture. It is called charging by conduction. It is when the negatively charged rod is touched to the knob of the electroscope, and the electrons are added to the electroscope, and as shown in the figure, the two leaves are charged negatively and repelling each other, therefore they spread it apart. And the process of the charging neutral object by bringing charged object near is called charging by induction, and the process of excess charge by connecting an object to earth is called grounding. Let's move on to the Coulomb's law. It is when the magnitude of the force between 2 point charges, which we can use QA and QB to represent it. A distance or the R is apart. We can write it as force is equal to K times by QA and QB over R square. And the electric force is the electric force is a vector quantity, which just mean there's in both they contain both magnitude and direction. But the Coulomb laws only gives the magnitude, but we can know the directions of the object from their charge, because if you can remember, the same charge will be the object with same charge will repelling each other, but the object with a different charge will be attract to each other. The SI unit for the Coulomb the Coulomb or the C is 6.24 times 10 to the power of 18 electrons of proton, and the charge on a single electron is actually equals to negative 1.6 times 10 to the negative of 19 Coulomb. Let's having a new term of elementary charge. It means the magnitude of the change of electrons, and charge on a single proton is actually equal to positive of 1.6 times 10 to the negative 19 Coulomb, which is going to mean that the magnitude of charge of electrons and proton is actually equal. Okay, so let's move on to the practice problems. The problem states that a sphere A with the charge of positive 6.0 mu Coulomb is located 4.0 cm to the left of the sphere B, which has a charge of negative 3.0 mu c, and the sphere C have a charge of positive 2.0 mu c, and it is 5.0 directly below sphere B. Find the net force on the sphere B. Okay, so let's write it down. What we know the QA, we know QB, and we know QC. We also know RAB and RBC. RAB is actually means that the distance between A and B, and RBC is actually mean the distance between B and C. Okay, so what we want to know is the F on the B. Firstly, we should draw a graph. As we can draw it, we draw graph from QA. We draw the pictures from QA to the QB, and then we have a line that represent the RBA, and we have the line represent RBC. And if you can remember, we also can find the net force by having a imagination line that is represent the F net on B, and we brings the formula that we have just know from the F is equal to K times QC times by QB over R of the BC square. We can find the FA on B, which going to be the 1.0 times 10 to the power of 2 Newton downward, and FC on B is equal to 2.2 times 10 to the power of 1 Newton to the left. And we find the F net by using the square root of A square plus B square, which is this A is going to be the FA on B, and B is going to be the FC on B. So after we converted it, we're gonna get the result of 1.0 times 10 to the power of 2 Newton, and we can find the theta by using tan negative 1 of FC on B over FA on B, and it's actually, after calculating, it's going to be 12 degrees. And if you can remember from the diagram we drew lately, the F net is going to be 1.0 times 10 to the power of 2 Newton at 12 degree below the x-axis. Why below the x-axis? Because if you can remember from the graph we draw, the location of the F net is actually going below the x-axis. Let's move on to the application of the electrostatic force. The electrostatic force is actually using for reducing air pollution by using it for the collecting soot in smokestack, and it also used in the photocopying machine. It is use of the static electricity to place the black toner on a page so that a precise reproduction of the original document is made. Let's move on to the essential question. The first one is asked about how does the electrostatic force depends on the distance between charges. So the answer would be that the electrostatic force is actually the electrical force is between two charges. Object is inversely related to the distance of the separation between two objects. The second question is asked about how can you charge an object by connecting and by induction. Charging by the connection is negative charge is rod is touched to the knob of the electroscope, and electrons are added to the electroscope, and the two leave charged negatively and repelling each other, which just means they're going to spread away. But the charging by induction is we can charging the neutral object by bringing a charged object near it. And for the last one of the section, what is Coulomb's law and how is it used? So firstly, Coulomb law is the magnitude of force between two-part object, two-part charge and a distance, 2-point charge and a distance. And the Coulomb law we can use by drawing diagrams that shows how the matter of charge relation to determine the directions. Okay, so that is all for the chapter 20. Thank you for listening. See you soon.